Problem number 4. How many positive integers not exceeding 2011 are multiples of 3 or 4 but not 5? Alright, now this is kind of a tricky problem, but if we just take it step by step, it's not so bad. And the first thing I'm going to do, I'm going to actually represent the sets of multiples of 3 and multiples of 4 in a Venn diagram, because that'll help me kind of organize my thinking. Alright, so let's call this the set of all multiples of 3. Okay, and then we have another set, and let's say this is the multiples of 4. Okay, so some of the multiples of 3 are also multiples of 4, like 12. In the same way with, the other way around, some multiples of 4 are multiples of 3. And if they're multiples of 3 and 4, then they would be in this intersection right here of the two sets. Okay, so some numbers like, say, 9, that's a multiple of 3, but it's not a multiple of 4, so it would be in this part of the Venn diagram. And, numbers like, say, 16 would be over here. It's not a multiple of 3, but it is a multiple of 4. And then numbers that are multiples of 3 and 4 are in the intersection. Okay? So that'll help us think about it. So the multiples of 3 or 4, so if a number is a multiple of a 3 or 4, then it's going to be a member of both sets and the intersection, right? Because if I have a number like 24, is that a multiple of 3? Yes. Is it a multiple of 4? Yes. So it is a multiple. It is a part of the part of both sets. Okay. If you have a number like 32, is it a multiple of 3? No, but it is a multiple of 4. So if you're looking at 3 or 4, so if this is true, then it's either gotta be a multiple of 3 or a multiple of 4. Okay, it doesn't have to be both, but it could be. All right. So the multiples of 3 and 4, 3 or 4, are going to be the combined set. If this was 3 and 4, then it would just be the intersection. Does that make sense? So let's take a look at that. Let's first of all look at the multiples of 3. Now that's not too bad. We'd have 3, 6, 9, and so on, all the way up. Let's find the biggest one. Let's find the biggest multiple of 3 that's less than or equal to, not exceeding, okay, 2011. So let's take 2011 and divide it by 3. So we have 6, that's 18, 21, 7, so that's 21, that's 0, and then we have a 1, so it's 670 with a remainder of 1. So 670 is going to be less than 2011, and 671 is going to be greater than 2011. So I'm not going to worry about multiplying that out. I could multiply that out, but I'm actually going to write it as 670 times 3. Okay, that's our last number, and I'm not going to worry about multiplying that out. Because if I then do the same thing to every number, if I divide every one of these numbers by 3, I'll still have the same number of numbers, and then but I'll be able to count them because my list will start with 1, and they'll just be incrementing numbers, right? So 1, 2, 3, and then if I want to count this last one divided by 3, 670. So there are 670 numbers between or positive integers, I should say, that are less than or equal to 2011 that are in this set. Okay, some of them are also multiples of 4, but I'm not going to worry about that right now. So there are 670. I'm going to write it on the line because that'll tell me that's the whole set, including the intersection. Okay, and so let's take a look at the multiples of 4. So we have 4, 8, 16, and so on, all the way up to something. Let's divide 4 by 2011, so that's 5, and then so that's 20, so what is that, 11, and so what would be 2, 502, that'd be 8, with a remainder of 3. Okay, so I know that 502 times 4 is going to give me something less than 2011, and if I multiply it by 503, it's going to go over. So I'm going to write this as 502 times 4. Okay, so then if I divide everything by 4, I can count them. Whoops, I must have done something wrong here. It doesn't go 4, 8, 16. It goes 4, 8, 12, right? Because these are multiples of 4. Okay, so 4, 8, 12. All the way up, divide this by 4, I have 502. Okay, so I have 670 multiples of 3, 502 multiples of 4. Okay, so I'm going to write that on the line over here, 502. But I can't just add those together because some of these numbers are duplicates, right? Like 12. 12 is going to show up in both lists, so I've double counted it. So I need to figure out how many numbers are in this intersection so that I can subtract the duplicates out, because I've counted these twice. Alright, so these are multiples of 3 and 4, so that means these are just multiples of 12, right? These are multiples of 12. So let's figure out how many multiples of 12 we have. We have 12, 24, 36, right? All the way up to what? Alright, we gotta figure that out. Let's divide 12 into 2011. And that'll go once, 12, 88, let's see, 81. And so then, let's see, if I take 6 times 12, I get 72, and I subtract, I have 9, and drop the 1, and so let's see, 7 times 12 is 84, and so I'll have some remainder here, but essentially this will be 167 times 12 will be my last multiple of 12. That's less than 2011. Okay, so again I can divide these all by 12 and then I can count them. So the last one will be 167. So I have 167 numbers that appear in both lists. Okay, so there's 167 members here. Okay, so if I want to find out the multiples of 3 and 3 or 4, okay, then I can add the multiples of 3 and the multiples of 4 and subtract the multiples of 3 and 4, okay, because we've double counted, so we're correcting for the double counting. Okay, so let's write that out. So multiples of 3 or 4 is equal to what? It's 670 plus 502, that gives us 1172, and then we have to subtract out the duplicates, that's 167, so that's 1005, okay? So these are the multiples, so we have 1005 multiples of 3 or 4. Alright, now we still need to take care of the last part of this. And we're not done yet because we want multiples of 3 or 4, but not 5. Okay, so there's some multiples of 5. So I'm actually going to draw another circle here to represent the multiples of 5. Ooh, that's kind of a lopsided circle, but you get the idea, right? So these are multiples of 5. Alright. And some of these multiples of 5 are also going to be multiples of 3, like 15, or 20 will be a multiple of 4 and 5, and then some will be multiples of all 3. Okay? So, in order to find the multiples of 3 or 4, but not 5, so we want everything in these two sets. Let me actually get a highlighter here. So we want everything in these two sets, but not in the bottom set. Okay, so we're looking for everything up here, okay, but not in that bottom set. So what we have right now includes this. Let me change colors here. So what we have right now actually includes this. Oops, this part here. Okay. Alright, so we actually want to subtract that out. Alright. So we need to figure out, so what, well, I guess first of all, what is that, what are these sets? So this football shape here, let's see, so this shape here, this represents the multiples of 4 and 5. So these are actually, let me get rid of some of this division here because it's getting in my way. Oops, there goes my circle. Hang on, redraw my circle. Let's see if I can draw it in here the way I had it. Alright, so this shape here, these are actually the multiples of 20, and this over here, these are the multiples of 15. But then we have this business here, okay, because these two sets overlap. So we have this piece in the middle, and what's that? Those are multiples of 3 times 4 times 5, which is multiples of 60. Let's see, can I draw that in here? I'll draw it off here. This is multiples of 60. So we need to subtract out the multiples of 20 and the multiples of 15, but add back in the multiples of 60. Okay, because we'll end up subtracting them twice. All right, so let's find out the multiples of 15 and 20, and that'll get us started. So 15, 30, and so on, all the way up to, okay, we got to do a division here. So let's take 15 into 2011. And let's see, actually, I got 134. I'm going to save a little time here so you don't have to watch me do my division. I got 134. So this is 134 times 15 is the last multiple of 15. So again, if I divide everything by 15, I'll have 1, 2, all the way up to 134. Okay, so we have 134 multiples of 15. Now, multiples of 20 look like 20, 40, 60, all the way up to what? Alright, well, 20 into 2011 is just going to be what, 100? So 100 times 20. Oops, 100. Okay, that'll give us 2000, which is the last multiple of 20. Alright, so if we divide everything by 20, then we get 1, 2, 3, all the way up to 100. So we have 100 multiples of 20. Alright, the last thing we need to look at is multiples of 60. Alright, so 60, 120, all the way up to, let's divide 60 into 2011. And what did I get for that? I got 33. Okay, so 33 times 60 is our last multiple. If I divide everything by 60, 1, 2, all the way up to 33. Okay, so, alright, so we want the multiples of 3 or 4, but not 5. So we have to subtract out all this stuff. Alright, so I know now, actually, let me get my eraser here. Because I actually want to write in this middle. Ah, there goes my edit, undo, erase. Alright. Well, okay, I'm going to write it with a different color. Alright, so this part here, if I pick up a green, so this is 33. Okay, can't really see that very well. And this whole thing here, the multiples is 130, 34. I'm going to switch back to black. That's kind of hard to see. So there's 134 in the whole set and 33 in the intersection, so this is 101.